There is a star about 640 light-years from here that should not still be in the sky. The last time astronomers got a good look at it, it had already started the process. The light I am watching right now left that star before the first human being picked up a piece of flint. Whatever it looks like at this exact moment in time, I do not know. Neither does anyone on Earth. The signal has not arrived yet. That is the thing about the universe that keeps me up at night. Not the distances, not the scale. It is the delay. It is the fact that the sky above you right now is a mosaic of different centuries. And somewhere in that mosaic, something has already happened that you will not hear about for another 1,000 years. There are 3 stars I want to tell you about. 3 specific, real, named objects in the night sky. They are there, right now, overhead, doing what they do, and what they are each capable of doing to a small blue planet with 7 billion people on it is not something I could have fully believed until I went out and looked for myself. Let me start with the one that is closest. Eta Carinae is not a subtle star. I want to be clear about that from the beginning. When astronomers point instruments at it, the readings come back strange. Too bright, too active, too much of everything. It sits about 7,500 light-years away in the constellation Carinae, and it is not one star actually. It is 2, a binary system, 2 massive stars in a long elliptical orbit around each other. And the larger one is one of the most massive and luminous objects we have confirmed in this entire galaxy. In 1843, it became the second brightest star in Earth's sky for a brief period. No explosion, no supernova, just a violent outburst, a great eruption that ejected something like 10 times the mass of our Sun into space and formed a pair of expanding lobes of gas and dust that astronomers today call the Homunculus Nebula. The star survived that. It should not have, but it did. The reason people study Eta Carinae very carefully is that it is considered a candidate for what is called a hypernova. Not a supernova, a hypernova. And I want you to understand the difference, because the numbers are the part that got to me the first time I looked at this. A standard core collapse supernova, the kind that happens when a large star exhausts its fuel and collapses, releases in a few seconds the same amount of energy our Sun will produce in its entire 10 billion year lifetime. That is already a number that has no meaning to a human brain. A hypernova is roughly 10 to 100 times more energetic than that. Some hypernovae produce gamma-ray bursts. These are the most energetic explosions we have detected in the observable universe. A gamma-ray burst from a collapsing massive star can, in a few seconds, release more energy than the Sun will emit across its entire existence. Stay with me here. If Eta Carinae produced a long gamma-ray burst, and if one of those jets happened to be pointed roughly in our direction, the effects at 7,500 light-years would depend a great deal on the angle and the intensity of the beam. Best current models suggest a direct hit from a nearby gamma-ray burst could strip away a significant fraction of Earth's ozone layer. We are not talking about the hole over Antarctica. We are talking about the shield that keeps ultraviolet radiation from sterilizing the surface. The cascade would not be instant. That is what I want to explain, because in every version of this story I have heard it told wrong. The gamma-ray burst itself would arrive at the speed of light. No warning, no time to prepare. The first indication anyone on the sunlit side of Earth would have would be a flash in the upper atmosphere. Brilliant, blue-white, lasting maybe 10 seconds. Then the chemistry of the stratosphere would start to change. Nitrogen and oxygen would be forced to combine in ways they normally do not. Nitrogen dioxide would form. The sky would turn a rust color, darker toward the horizon. It would not look like an emergency at first. It would look like a strange sunset that never quite ended. The ozone loss would unfold over months. The UV flux at the surface would climb. The effects on marine phytoplankton, the base of the ocean food web, would be significant. These are not dramatic images. Phytoplankton are invisible, but they produce roughly half of Earth's oxygen and form the bottom of the food chain for most life in the ocean. A collapse at that level propagates upward. There is a hypothesis, and I want to be honest that it is not settled science, that a gamma-ray burst from somewhere in our galaxy may have contributed to the Ordovician mass extinction, roughly 440 million years ago. That event wiped out around 85% of marine species. The idea is contested, but the people who argue for it are not fringe researchers. They are working from real models of how atmospheric damage from a gamma-ray burst would interact with the climate and biosphere. The honest thing to say about Eta Carinae is this: the probability in any given century of it producing a gamma-ray burst aimed at Earth is small. Current estimates suggest the jets are probably not pointed at us. The geometry may spare us entirely, but it is out there, 7,500 light-years away, building towards something, and no one alive today will know what it decides to do. That one still gets me. Not the probability, the not knowing. Let me tell you about the second star, because it is different in a specific way that makes it, in some respects, more unsettling. Betelgeuse is familiar. You may have watched coverage of it in late 2019 and early 2020 when it dimmed noticeably, dramatically enough that even casual observers noticed it had changed. People talked about it for months. The phrasing was always some version of, "Is it about to explode?" And the answer that came back from astronomers was careful and a little maddening. Maybe. Possibly not yet. Eventually, certainly. Here is what Betelgeuse is. It is a red supergiant, one of the largest stars visible to the naked eye. If you placed it at the center of our solar system, its surface would extend somewhere past the orbit of Jupiter. It is enormous in a way that is genuinely hard to visualize. It sits about 700 light-years away, and it is dying. The dimming event in 2019, which the astronomers who studied it eventually called the Great Dimming, was likely caused by a mass ejection. A large, hot blob of plasma erupted from the star's surface, cooled as it moved away, and condensed into a cloud of dust that blocked some of the light. The star was not actually dimming. It was hiding behind its own debris. But the underlying fact remains. Betelgeuse has exhausted its hydrogen fuel. It is burning heavier elements now. Stars do not last long once they reach that stage. On cosmic timescales, it is extremely close to the end. We are talking possibly within the next 100,000 years, possibly sooner. Astronomers have said publicly that they would not be surprised if it happened within their lifetimes. I want to be careful not to overstate that. It might not, but the stage is set. When Betelgeuse goes, at roughly 700 light-years, it will be visible in daylight. It will be bright enough to cast shadows at night. It will not be a flash. It will be a slow brightening over days and weeks, then a long fade over months, a remnant glowing for years. Your grandchildren, or their grandchildren, or someone down that line may wake up one morning and find a second sun in the sky. At 700 light-years, the gamma-ray burst risk is lower than with Eta Carinae. The distance provides some buffer, and current modeling of Betelgeuse's rotational axis suggests its poles are not aimed at Earth. The more likely outcome for us is a spectacular and scientifically extraordinary event, a new nebula forming over centuries, and no direct harm to the planet. But I always circle back to this. The light I see when I look at Betelgeuse right now left that star approximately 700 years ago. If Betelgeuse exploded the year you were born, the light from that explosion has not reached us yet. We would not know. We are watching a dead star and calling it alive, because the light from its death has not arrived. I find that genuinely strange, every time. The third star is the one I spend the most time thinking about. because it is different from the other two in one critical way. It is not a distant, exotic monster. It is the reason you are alive. Our Sun is a middle-aged, relatively quiet G-type star. It is not massive enough to produce a hypernova. It is not in any late-stage dramatic phase. By stellar standards, it is calm, consistent, unremarkable. We depend on that consistency for everything. Every crop, every weather pattern, every ocean current, every breath. The Sun is not going to explode in any human-relevant time frame. That is not the threat. The threat is smaller, more frequent, and much harder to predict. The Sun produces solar flares. It produces coronal mass ejections, massive clouds of magnetized plasma launched from the Sun's surface at speeds between 250 and 3,000 kilometers per second. Most are minor. Most never intersect Earth's orbit. The magnetosphere deflects the rest. We get auroras, beautiful, harmless light. But in 1859, something different happened. On September 1st of that year, an astronomer named Richard Carrington was doing routine solar observation. He watched an intensely bright flash on the Sun's surface. Around 17 hours later, the largest geomagnetic storm in recorded history struck Earth. Telegraph systems across Europe and North America failed. Some telegraph operators reported receiving electric shocks from their equipment. Some systems remained operational after operators disconnected power, running on the induced current alone from the geomagnetic disturbance alone. The aurora borealis was visible as far south as Cuba and Hawaii. That was 1859. The telegraph was the most advanced technology on the planet. I want you to think about what a Carrington-level event would mean in the present day. Not 1859. Now. Power grids are vulnerable to geomagnetically induced currents in a way the telegraph was not, because modern grids are continental. Long, high-voltage transmission lines act as antennas for the induced currents from a major geomagnetic storm. Transformers at the nodes of those grids, large, heavy, custom-built machines that take over a year to manufacture and are not stocked in large reserve quantities, can be damaged or destroyed by sustained geomagnetically induced currents. A study commissioned by the United States government in the early 2000s estimated that a Carrington-level event today could damage or destroy a significant portion of high-voltage transformers across North America. Recovery time estimates have ranged from months to years. That is not a power outage. That is a sustained loss of electrical infrastructure across entire continents. The cascades from that are not complicated to trace, just uncomfortable to follow. Water treatment systems depend on powered pumps. Food distribution depends on refrigeration and fuel logistics. Hospitals depend on power. Communications depend on infrastructure that depends on power. Satellites, which depend on nothing but the physics of orbital mechanics, would survive. But the ground systems that communicate with them might not. A small team of physicists and space weather researchers who study this professionally have argued for years that the risk is underestimated and underprepared for. Not because a Carrington event is likely in any given decade, but because the consequences are so asymmetric. A 1 in 100-year risk of a multi-year civilizational disruption is worth taking seriously. In 2012, a Carrington-class coronal mass ejection did occur. It missed Earth by 9 days. The Sun released it into space, and the planet moved through a different part of its orbit in the time it took to arrive. 9 days. I have looked at that number a few times now. It does not get easier. Now, this is where I want to slow down, because I think there is something important in all three of these. Eta Carinae, Betelgeuse, the Sun. 3 different mechanisms, 3 different timescales, 3 different orders of probability. What they share is this: they are natural systems operating exactly as natural systems do. They are not malfunctioning. They are not hostile. A gamma-ray burst from a dying hypermassive star is not aimed at us. A solar flare from our own star is not a punishment. The universe is not doing any of this at us. I think about this when I am out there in the dark, away from everything, looking at the stars as light sources rather than mythology. There is something that functions like comfort in the neutrality of it. The universe does not know we are here. It does not care. But not in the cold way that phrase usually implies. It just does not have that category. Caring and not caring require a mind, and the universe does not have one. It is just doing what mass and energy do. We built cities under a star. We built calendars from its behavior. We wrote poetry about the other lights in the sky. We looked at a universe that is mostly plasma and radiation and empty space, and somehow found a way to make music. That has always seemed to me like a remarkable thing to have done, given the circumstances. The science says this plainly. The sun will not undergo a catastrophic explosion in any time frame that threatens human civilization through stellar death. Betelgeuse, when it goes, is far enough away and oriented in a direction that current models suggest we will be observers, not casualties. Eta Carinae is more uncertain. The geometry of its jets not fully resolved, but most researchers consider it unlikely to produce a beam intersecting Earth. The real risk, the one that is not speculative, is space weather from our own sun. A Carrington-level event, or something more severe, is a matter of when, not if. Solar physicists do not disagree about this. They disagree about timelines and probabilities, but not about the nature of the risk. And unlike a hypernova 7,500 light-years away, this is something we could partially prepare for. Grid hardening, surge protection for key transformers, early warning systems using satellite monitors positioned upstream in the solar wind. None of these are science fiction. Some of them are already partially deployed. The gap between partially prepared and adequately prepared is the part that sits with me. You are somewhere on Earth right now. Maybe it is night. Maybe you can see a few stars through whatever window is nearest to you. Or maybe the city lights have washed them out, and all you see is a uniform orange glow above the rooftops. Either way, the sky is there. Eta Carinae is in it, working through whatever phase it is working through. 7,500 years of light travel away. Betelgeuse is in it, its core burning through silicon and iron, counting down on a clock none of us can read. And the sun is there, on the other side of the horizon, cycling through activity in 11-year rhythms that have been going on since before our species existed. Most nights, I find that beautiful more than I find it frightening. The fact that any of this works at all, that the distances are right, that the sun is quiet enough, that the planet is here, that there is something looking up and noticing. That still strikes me as the strangest thing in the universe. Not the danger. The precision required for the danger not to have already won. If you want to sit with me through another one of these, the next one is about what would actually happen to Earth if the moon were simply gone. Not exploded, not moved, just quietly removed one night, and what the planet does in the hours and years and centuries after it discovers the sky is darker. I will see you there.